In this video, I would like to wrap up our recent tour of compact sets by discussing some consequences of the Bolzano Weierstrass theorem from Real Analysis 1. So to remind you of what that theorem said, it told us that any bounded sequence of real numbers yields a convergent subsequence. So the first thing I want to point out is that you can take that result and extend it to Rn, so that any bounded sequence in n-dimensional Euclidean space must have a convergent subsequence. I'll say a little bit more about it in a moment, but I'm not going to do a rigorous proof of that statement because it's an exercise I give my students. Then I will prove for you the Heine Borel theorem, which tells us that a set in Rn is compact if and only if it is closed and bounded. We have already shown that in any metric space, Euclidean or not, a compact set must be closed and bounded. So this allows us to go the other direction, which is not true in general. So this is a result for Euclidean space. Then we will revisit the notion of being complete. So I will say that with this version of the Bolzano Weierstrass theorem, we can prove that Rn is a complete metric space. Okay, let me say a bit about this before we move on to Heine Borel. You should have proved in Real Analysis 1, when you first learned about sequences, the regular Bolzano Weierstrass theorem. So any bounded sequence of real numbers yields a convergent subsequence. Now imagine that you have a bounded sequence in R3, just for illustration's sake. So you have a sequence where the individual members have 3 coordinates, call them x, y, and z. If the sequence of vectors in R3, you could think of them as, is a bounded sequence, then each of the coordinates is bounded. We've actually proven that kind of statement. So if the sequence is bounded, all of the coordinates are bounded. So what you can do to generalize Bolzano Weierstrass on R to Bolzano Weierstrass on Rn is from your first sequence, the original bounded sequence, pass to a subsequence so that the x coordinates converge. So you could say, hey, the x coordinates are bounded, so I can extract from the sequence in R3 a subsequence in R3 where the x coordinates converge. You want to do that first. Now throw away the original sequence and focus on your new sequence where the x terms are converging. Step over to the y terms. Those are bounded, so you can pass to a subsequence of your subsequence so that now the first 2 coordinates converge. Throw away the second sequence that we had. Now we have a sequence bounded in R3 where the first 2 coordinates converge, pass on to the z coordinate. So that's the idea of the proof. I pretty much did it out loud just now, but you just want to write that down. And the trickiest thing about working with sequences in Rn is the notation with subscripts and superscripts. So if you're actually doing this, be careful. Let's take a look now at Heine Borel. This is a very short proof. Both of these proofs are actually very short once you have Bolzano Weierstrass, which we will now take as fact. So let's do Heine Borel. Since closed and bounded, I think, is the easiest thing to eyeball about compact sets in Rn. So open cover is pretty tricky. Sequential compactness may be a little easier, but I think that if I hand you a set in Rn, it's easiest to determine if it's closed and bounded. So we'll do a couple quick examples, actually all on the Euclidean real number line, I believe, where we'll be able to say, hey, the set is closed and bounded, or it isn't, and therefore it's compact. So we'll have a few examples. And then we'll talk about completeness. And then what I want to do is kind of go all the way back to day 1 of real analysis, because if you're watching this as second semester real analysis, I want to trace all the way back to what I treat as the starting axiom for the study of real numbers, which for me is the supremum property. And I just want to trace out a rigorous, logically correct path from the supremum property through these results. Because at this point, we are referring back to so many earlier results and results from Real Analysis 1, I just want to show you the logical flow from our starting axiom through these results on n-dimensional space. As I said a moment ago, in order to prove the Heine Borel theorem, we only need to prove one direction of this if and only if statement, because we have already shown a stronger result that in any metric space, every compact set must be closed and bounded. So the result we need to establish is that in Rn, if a set is closed and bounded, that's enough to know it's compact. Not true in general, but true in Rn. So imagine that A is a compact subset of Rn. Let's just do this proof, it's fast. Suppose A subset Rn is closed and bounded. I haven't brought up this result yet, but I will add it to our map of major results that we do at the end of this video. which is the equivalence of compactness and sequential compactness. Since we know that if a set is sequentially compact, it's compact, and I think it's easier to work with sequences than open covers, what I'm going to do is prove that this set A must be sequentially compact. Therefore, I want to show that any sequence in A yields a subsequence which converges to a limit in A. So our next step is to imagine we have some sequence in A. Let xn be a sequence in A. Since A is bounded, this is a bounded sequence in Rn. By the n-dimensional Bolzano Weierstrass theorem that I just kind of talked through, this sequence must yield a subsequence which converges to a limit in Rn. Thus, there is a subsequence, which I will denote as x sub n sub k, converging to x naught in Rn. This is the limit of a sequence which lives in A. We have a result saying that that places this limit in the closure of A. So thus, x naught belongs to the closure of A. But A is closed by hypothesis, so that's really a roundabout way of saying that this limit belongs to A, and now we're done. So because we have established at this point that every sequence in A has a subsequence converging to a limit in A, this set A is sequentially compact. So A is sequentially compact. Whoops. Sequentially compact and therefore compact. This result that we've just proved is very useful when you look at examples in Euclidean space. So I'll step aside in case you're still writing this down and thinking about it. Then we will look at some subsets of the real number line, and we will use this characterization of compact sets on R in order to ascertain whether or not our examples are compact or not. It's going to be very fast because I think for each one, it's pretty clear if it's closed and bounded or not. And here are those examples. So these are subsets of the real number line. In fact, I think they are all examples that we looked at when we learned the definitions of compact and sequentially compact. So I would like for you now to reach the same conclusion again based on the Heine Borel theorem. So look at each of these. Are any of these sets both closed and bounded? Because if they are, they're compact. If they're not compact. If you'd like to, you could also assess them from the other points of view. So are they sequentially compact? And you can also try to think about open covers as well. Give yourself a couple minutes to work through these, and then I will come back and just quickly come up with the correct conclusion based on the Heine Borel theorem. All right, let's go through the results out loud. So the first example is the open interval from 0 to 1. That's bounded but not closed, so it's not compact. For the second one, it is both bounded and closed, so it is compact. The set of rational numbers is neither bounded nor closed, so it's not compact. And if I took this set and I tried to bound it, so say I took rationals between 0 and 5, that would be bounded, but it still wouldn't be closed, so that would also not be compact. Integers is closed but not bounded as a set, so that is not compact. However, if I take a bounded subset of the integers like 0, 1, 2, then that's both closed and bounded, so it is compact. And then lastly, the Archimedean set is the trickiest one here. It's certainly bounded, and if you haven't worked through this or haven't looked at it recently, it feels closed at first if you think of it as like discrete isolated points. However, there's an accumulation point at 0 which does not belong to the set, so it is not closed and therefore not compact. All right, I hope working through these examples from this new perspective with Heine Borel demonstrates how useful Heine Borel is when you're working with compact sets in Euclidean space. Let's now change gears for a moment, and we will look at the completeness of Rn as another consequence of the Bolzano Weierstrass theorem. Now, with all of the results that we have, we are ready to prove that a sequence in Rn, which is Cauchy, converges. In other words, Rn is a complete metric space. I'm going to do the proof. It's pretty fast, but at this point, we have so many pieces of information that we're relying on that after we're done proving this, we will just make a map of theorem. So it'll just be a quick kind of chart starting from the supremum property and ending up here. We want to prove that if xn in Rn is Cauchy, then it converges. So I think the first sentence in our proof should be let xn be a Cauchy sequence in Rn. In fact, let me write let xn, which is a sequence in Rn, be Cauchy. We want to prove that this converges to a limit. So for that, we need a candidate for what the limit could be. Here's how we get that from Bolzano Weierstrass. Because xn is Cauchy from an earlier result, we know that it's bounded. Therefore, Bolzano-Weierstrass implies that there is a subsequence of this which converges to a limit in Rn, and that's going to be the candidate for the overall limit. So by Bolzano-Weierstrass, I'll write in shorthand that there exists a subsequence which converges to a limit, which is an actual point in Rn. And again, it's like, until I wrote this down, it wasn't clear at all what this could possibly converge to because we don't even know like what the sequence is. So I have to have a proposal for what the limit would be. And this is what I'm going to propose. Okay, let's keep going. And then I want to make some remarks about this proof. So since xn is Cauchy, it's bounded. So we know that there exists a subsequence which converges to that point. We are now going to do a proof of sequential convergence, which is going to be given some choice of epsilon. We need to identify a threshold index capital N so that the infinite tail of the sequence beyond that is within distance epsilon of the limit. So probably the next sentence we should write is let epsilon be greater than 0. Since xn is Cauchy, there exists a threshold index capital N from the natural numbers so that whenever two random indices, which I will order as little m greater than or equal to little n greater than or equal to the threshold, we have that the distance in Rn from the nth term to the nth term, nth term to the nth term, sometimes those sound the same. Normally, for just regular Cauchiness, you would write epsilon, but we're going to do a triangle inequality argument here. So I'm going to insist that this threshold is large enough so that this distance is less than an even smaller distance, smaller than epsilon, epsilon over 2. Okay, so here I've picked a threshold so that pairwise distances beyond that threshold are smaller than epsilon over 2, and that is going to be the threshold for the entire sequence. The catch is that if I compare a random term from the sequence, so these terms, they're not specified, but they could just be from the sequence. They're not necessarily from the subsequence. If I want to take a random term from the sequence and compare it to this limit, I need to compare each of those individually to something from the subsequence, because the subsequence is what we have a good handle on at the moment. I'm not going to pick another threshold because I really just need to grab one specific subsequence term. I don't need to be more general than necessary here. So let me say choose an index in sub capital K beyond this threshold so that the distance from that term to the limit of the subsequence is also less than epsilon over 2. So this here is specific. This is just one particular term. The idea is, given our choice of epsilon, pick this threshold, and then you can always go beyond that in the subsequence. So just go beyond it, grab a term from the subsequence beyond that threshold, and claim it's going to work for our triangle inequality argument. So we don't need to be too general with how we pick our subsequence term. Okay, I think to best understand this proof, it's illustrative to try to finish it on your own. So let me pause here. We have the two elements of the triangle inequality that we need. So see if you can finish this. And then when I come back, I'm going to try to do it right here so that I don't have to erase anything. All right, let's finish this. Now I just want to grab one random term beyond the threshold. So then for any index little n beyond this threshold, we have that the distance from xn to x naught, oh, can I do this here? Maybe, is less than or equal to. It's like I'm going to have xn be one of the terms in this Cauchy comparison and the subsequence term be the other. Here, these are just random terms beyond the threshold, and now I'm just going to identify one specific choice from this pair as the subsequence term. Okay, so let's see if I can fit this on here. This is going to be less than or equal to comparing xn to xnk, and then also comparing xnk to the limit. Let me drop down here. Each of these is less than epsilon over 2. That's how we chose our threshold. Okay, sorry to squeeze this in here like this. If you have room, write one more sentence, which is, therefore, xn converges to x naught. I think this is kind of a neat proof because when you just know your sequence is Cauchy, what you're missing is the limit. So it's like we have to figure out how to identify the limit, and we get that here from Bolzano Weierstrass. I want to point out, and this is going to go into our map of results, that this statement here is calling back to something that we have already proved, which is that Cauchy sequences are bounded. That needs no earlier results. The fact that Cauchy sequences are bounded comes straight from the definition of a Cauchy sequence. So given the definition of a Cauchy sequence, you can literally construct a bound. You don't need to refer to any previous theorems or anything like that. So this isn't really like calling back to any prior results. This is something that you can just immediately prove from the definition of Cauchiness. And then we have Bolzano Weierstrass, the theme of the video. And then the rest of it is just checking that the definition of convergence is being satisfied given that we have a Cauchy sequence with a convergent subsequence. All right, we are done proving things. So in a moment, I'm going to come back and I'm just going to put up a chart. I just want to start with the supremum property, which is like my day one axiom of real analysis. And I just want to trace all of the results that we've needed in order to get to this point. There are plenty of theorems that you prove along the way that we're not going to put up. I just want to focus on what goes into the results that we saw today. Okay, I just want to take a moment to go all the way back to the supremum property, just to trace through to the results that we have, because in both of those proofs, we cited earlier results, which might have cited earlier results. And so there's always this feeling of like, are we being circular, or is everything kind of proceeding in a way that builds up from our starting axiom? Now, the supremum property, that is what I introduced the study of the real numbers with. This says that every set of real numbers which is bounded above has a least upper bound. It's what allows you to think of the Euclidean real number line as like a continuum with no holes. With the supremum property, so I'm going to start my chart right here, we prove something called the nested interval property. The nested interval property says that if you have closed bounded intervals, which are non-empty and which are nested, so maybe this is your first one, and then you move in, and then maybe you only move in a little bit, like that. If you have an infinite family of nested closed bound intervals of this form, they have a point in common. So they do have some element which survives the intersection if you look at taking the intersection of this family of sets. That relies on assuming that, say, the set of left sides of your intervals have an upper bound and therefore a least upper bound. So it relies on the supremum property. And then the nested interval property goes into the proof of Bolzano Weierstrass on R. Typically, when you prove Bolzano Weierstrass on R, you say, okay, your sequence of real numbers is bounded, so enclose it in a closed bounded interval. And then you start bisecting the interval. You kind of, I'm not going to do the proof right now, but you basically zoom in by cutting your closed bounded intervals in half until you basically say that your sequence is going to have a subsequence which is clustering up to something. And it only relies on the nested interval property to get that. And then, as we talked about today, from Bolzano Weierstrass on R, you can generalize it to Bolzano Weierstrass on Rn. So far this is just one straight progression. You could do this all in one sitting. Then let me put over here the Heine Borel theorem that we looked at today. Bolzano Weierstrass on Rn leads to Heine Borel together with, kind of off over here, the idea that a set is compact if and only if it is sequentially compact. This result is not part of this kind of vertical chain of results. This is something that's true about metric spaces. So in any metric space, a set is compact if and only if it's sequentially compact. So it's not part of our study of the real numbers. So with that, we proved Heine Borel. We also proved that Rn is complete. And again, to get that, we brought in a result which is true in general metric spaces, which is that Cauchy sequences are bounded. I'm smiling because this proof is a ton of work and this one is like 3 lines. So there's a big difference here in the amount of work you have to do off to the side. But that's it. So this is how you can start at the supremum property and get all the way to the Heine Borel theorem and the fact that Rn is complete and all of the results that you really need along the way. There's a lot of work here, but everything you do here is valid in general metric space settings, including those which do not have a supremum property. So this is a fair result to kind of feed into this work. Last thing I want to say before I end this lesson is that when we talked about Cauchy sequences, I said, oh, that Rn is complete is like your axiom on R. And I am now tracing this back to the axiom that I like to study real numbers with, the supremum property, and kind of showing how it's a consequence of that. There are different routes that you can take through this material. So this is how I progress through this material. It's possible to do it differently. So there are different ways to have an axiom up here, which is why we say that all of these axioms are essentially some kind of completeness property. So the supremum property could be called a completeness property because it implies the completeness of Euclidean space. Okay, I think I've said enough on this subject. Again, I hope that this chart was helpful if you've been trying to remember like how much of the earlier results you needed to recall in order to get to the 2 main results that we have today. We are just about done in Real Analysis 2 with our study of topology. Up next, maybe in a video or 2, will be functions. So we'll start to introduce the idea of taking the limit of a function, functional continuity, with an eye towards eventually moving to differentiability, integrability, that sort of thing. So our study of topology was hopefully fun, challenging possibly, but we are moving towards now looking at functions. Okay, thank you for your attention.